Thanks, Chad. Hi, my name is Ying. I'm a software engineer working on the YouTube live streaming infrastructure. So today I'm going to talk about how we use WebRTC in YouTube live streaming. So first I'm going to talk about how WebRTC fits into the picture of live streaming. And then I'll go into a little bit more details on how we implemented both the server and client sides for live streaming using WebRTC. We know that WebRTC is commonly used for peer-to-peer video chat or video conferencing. In these applications, media data flows in both directions between users. And you can scale it a little bit to make multi-party conferencing, either using mesh network or using a centralized solution. But there is still some limitation to the scale you can achieve. In live streaming, however, media data flows in one direction from the creators to the viewers. And in this case, the viewers are in a much larger scale, in the order of thousands or even in millions concurrent viewers for a single stream. At this scale, you need servers and you need a content delivery network to distribute the video data. And we use HTTP-based protocols for delivery. But today I'm going to focus on the ingestion part of live streaming. I'm going to talk about how we use WebRTC as an ingestion protocol. There are different ways creators can do live stream to YouTube. On desktop, initially we have the Stream Now and events-based options to go live. These two options uses RTMP protocol for ingestion. RTMP stands for Real-Time Messaging Protocol. It is a relatively old protocol owned by Adobe, but it is pretty popular. Many streaming providers, software encoders, and hardware encoders support RTMP for live ingestion. But you do need to install a third-party software or use a standalone hardware encoder in order to go live stream. And you also need to do some configuration on those encoders. And this may be too much trouble for some creators who just want to go live very quickly. That's why we added the webcam-based live stream option. This takes the advantage of the browser support for WebRTC. And as a result, users do not need to install any extra software. With a few clicks, they can go live just through the web browser. We also added mobile live streaming on Android and iOS in the YouTube main app. So these are in the native app, not browser-based. And this is also based on WebRTC. Live streaming is especially useful when the creators want to walk around while doing the live stream. So the reason we use WebRTC as an ingestion protocol instead of RTMP in webcam and mobile live stream are, first of all, as I mentioned earlier, it is much easy to set it up because of the browser support. So users do not need to install third-party software or use a hardware encoder. Secondly, WebRTC has very active protocol development. One of the advantage of that is it supports newer codecs such as VP9 and also AV1, as Chad just mentioned. On the other hand, RTMP doesn't have active protocol development, so there's no standard way to add new codecs into it. WebRTC also has end-to-end encryption, which is important, whereas RTMP has limited encryption option. WebRTC is also UDP-based, hence it has low latency, and RTMP is TCP-based and has relatively higher latency. In our experiment in our mobile live stream, we saw about 20% reduction in latency in WebRTC when compared to RTMP. Another big advantage of WebRTC is that it has built-in bandwidth estimation and adaptive bitrate. This is very useful for mobile live streaming because the network can change very quickly when users move around. So WebRTC will do dynamic resolution change or frame rate change when the network condition changes. When network condition is poor, it will lower the resolution or frame rate. But RTMP doesn't have these features. That's why it's not very feasible for to use RTMP under poor network condition, unless you add a very large player buffer, but that will increase latency. So media quality and smoothness in playback and latency are the important metrics we look for in a live stream, and same as a video chat, actually. So in the ideal world, we would want good media quality, low latency, and very smooth playback. But it is very hard to achieve, especially when the network condition is poor. So we need to make trade-offs. WebRTC, in some conditions, is pretty aggressive to trade off media quality in order to maintain low latency and smoothness. And it is understandable because WebRTC is optimized for real-time interaction for video conferencing. And so to read into this diagram, basically, the closer it is towards the size of the triangle, the better the metric is. So you can see that WebRTC has low latency, high smoothness, but relatively low media quality when network condition is poor. And RTMP, on the other hand, has relatively higher quality, but would have higher latency and worse smoothness in playback when the network condition is poor. And also, the trade-offs you want to make among these metrics also depends on the application. That's why in our Stream Now option for live streaming, we give users the different latency classes for them to choose depending on their application. The normal latency choice is good for cases when you want high quality and high resolution. And it can be applications that don't require much interaction between the creators and the viewers. For example, when you want to live stream a music concert or news broadcast. On the other hand, if you want real interaction between the creator and the viewers, then you would want lower latency. For example, a lot of gamers, they like to do live streaming of their gameplay, and they also want a lot of interaction with the viewers through chats. For the mobile live streaming and webcam live streaming options we do fix the latency class to low and ultra low latency, because for these cases, we do see that most of the time creators want to interact with viewers a lot. So next, I'll talk a little bit more on how we implement both the server sides and the client sides to use WebRTC for live streaming. So first, the clients will send a HTTPS-based handshake signaling request to the WebRTC ingester server. So this is pretty standard in WebRTC. The handshake request will contain the session description protocol, SDP. And the WebRTC ingester server basically uses a WebRTC library and creates peer connection with the clients. It will send back the answer SDP that contains the ICE candidates that the client will use to connect. Once the connection is established, the clients will send the media data to media front-end services. And the media front-end will pass the packets to the WebRTC ingester. A media front-end is there because they are more widely deployed and they are closer to the users. And then the WebRTC ingester server pass the video data to the transcoding service. The transcoding service decodes and re-encodes the video data into different resolutions. And then the content delivery network will distribute the video data into the viewers and choose different resolution based on the bandwidth of the viewer's network. So on the server-side implementation, it's basically the WebRTC ingester that's handling the WebRTC protocol. But we do need to do some customization. First, because the clients are not sending the media data directly to the WebRTC ingester server, so we do not send the IP address and port of the ingester server back to the client. We need to send the media front-end server's IP address and port to client. That's why we need to create a custom port allocator to supply to the WebRTC, to the peer connection factory. And second, we also need to supply a customized video decoder factory to the peer connection because we want to create a no-op video decoder. This is because we already have a transcoding service to decode and re-encode the media data into different resolution. So we don't want to decode and re-encode that again in the WebRTC ingester server. Another customization we made is to provide a fake audio device module to drive the audio processing. Because in a normal peer-to-peer situation, the end device has the audio hardware and device to play out the audio, and that's what driving the audio processing. On the server side, though, we don't have these audio device and module to play out audio. That's why we need to provide a fake one to drive the processing.
So my question is you have the media front end between the clients and the WebRTC ingester. So will that add additional delay, latency?
Maybe a little, but it's not much.
Okay.
Yeah, and also the media front end is the purpose there is really to be very close to the user, and that actually does helps a lot. In reducing.
Yeah, maybe there is another question. So, so what is the you mentioned there is ultra low latency. So, what is the real latency you guys have? YouTube can achieve? Just roughly how many seconds? Like.
Well, it is
on the ingester side.
Ingester side. Yeah. So it is hard to give an exact number here because this really depends on the client's network and also the devices.
Okay, okay.
But we're trying to, it's on the order of like around 2 seconds.
Oh, 2 seconds, okay. 2 seconds on the ingester.
Not just the ingester, I mean on the servers, before the delivery.
Okay, okay.
And yeah,
thank you.
So we actually have 2 more talks we need to fit in after this one. We're really supposed to be at around 9, so we're kind of tight. I do want to allow questions, but I'd rather let Ying go through her presentation and do it in a relaxed mode rather than trying to rush through things. Thanks.
And there are also some customizations we can do on the client side. So first, the client actually doesn't need to collect the ICE candidate because for live streaming, the media flows in one direction. So the server doesn't need to know client's IP and IP address and ports to send media data to client. Also, we don't need stun or turn server here because the servers are always reachable. On the client side, we can also change the codec preferences. And the SDP that's sent through the handshake, there is a media video line that has a list of numbers that corresponds to codecs. For example, here, 96 corresponds to VP8 and 98 corresponds to VP9. So if you move 98 to the front, then the WebRTC will prefer to use VP9 instead of VP8. And we found that hardware VP9 and H.264 performs better than VPA, and so we use VPA as a software fallback. Also, for H.264, it can have different profiles. For example, the constraint high profile has better quality than baseline, and by default, it is ordered in front of the baseline profile in SDP. For native apps, you can actually reorder the codec through the API instead of manipulating SDP, which is always kind of brittle. So the native API does allow you to inject video and audio encoder or decoder factories. So for example, in the video decoder factory, you can exclude some video codecs. This can help you to reduce your mobile app's binary size. And the order you specify the video codecs also defines the preference you want for those codecs. And you can also specify when to use software fallback. In mobile clients, we also have customized video capture to add image filter effects. And as I mentioned earlier, WebRTC is pretty aggressive to trade off media quality in order to maintain low latency, because it really needs a sub-second latency. But for live streaming, we can afford a little bit more latency, and we have some buffer in the player to hide some ingestion gaps. That's why we did some tuning on the client side to adjust some bandwidth estimation parameters and initial bitrate estimation in order to improve the quality a little bit. And in our experiments, we did get at least greater than 10% increase in watch time per playback after the tuning. On the audio quality side, because WebRTC is, by default, is optimized for conferencing, so it has like noise and echo cancellation. But for live streaming, we can have any kinds of audio. Maybe we have background music. We can have non-speech audio. That's why we don't want to filter out any audio. And as a result, we disable the echo cancellation, noise suppression, and keyboard noise detection. So in summary, to use WebRTC for live streaming, you do need some customizations, both on the server and client sides. And there are quality and latency trade-offs you can make depending on your applications. And finally, I think the active development in WebRTC is a big plus for us to use it as an ingestion protocol. And I believe that the very active community around WebRTC is a big driving force to make WebRTC better and better as well. Thanks.
Great. Thank you so much, Ying. I think actually we can probably just take one or two questions, preferably on the quicker side of things. Any questions?
How do you do the no ice server? The no stun and the no ice, is that in WebRTC or is that?
Yeah. So yeah, just so everyone can hear. So the question was, how do you get away without using without using ice?
We do use we do exchange, like the server does send ICE candidates to the client, but the client doesn't need to send ICE candidate to the server because the server doesn't need to know. Server doesn't need to send data.
Right.
So I mean, you can in the API, I think you can skip the ICE collection step.
Okay.
All right, one more. Yeah. Let's go. Yeah, come off the mic, please.
Have you considered using WebRTC to deliver content back to the client? So you'll have WebRTC streaming to Google, and Google has some sort of broadcaster which will stream RTC stuff to peers who is viewing content.
So
instead of doing all this transcoding, all this hard work, instead of like converting this stuff, you can just use WebRTC to deliver real-time content to the clients. Have you considered this?
I think the question here is how scalable it is. So
yes,
yeah.
but essentially it should be easier to scale because you just need to restream the same stuff that you got from the client, and you don't have to transcode, so you don't have to waste CPU time. It could be done using even simpler hardware than, because you don't have to transcode stuff, you just need to rebroadcast stuff.
Now that's an interesting point, but we haven't considered that yet.
You know, just as a given answer, I mean, for a lot of that, we're looking at, like, how can you stream it out to 2 million, 5 million people at once? So a lot of what we're trying to do is trying to make it so that, you know, first of all, that people can watch any stream in any condition. So if you're, like, looking on a 4K television, you could get the full 4K, 60 frame per second experience. But if you're sitting in a red line, you know, stuck in one of their signaling delays, you could still watch it at a much lower resolution and still watch the same stream. So a lot of it is, first of all, optimizing the resource around, like, producing all those versions so that we could quickly upsample and down based on network conditions and do it efficiently across millions of people instead of having to, you know, re-sample and retranscode for each individual user. And, you know, there's also, you know, we have a huge content delivery network with all sorts of edge caching and other things that are fully optimized around the idea of using less ISP network around making it so we could serve, like, millions of people, you know, in you know, various cities around the world without having to regenerate things off our core servers. So a lot of it is fitting in what YouTube is already excellent at in our VOD world, but making it so that we can, you know, get that lower latency stream coming into us.
Okay. Unfortunately, we're tight on time. Thank you so much, Ying. That was great.